Hello everyone and welcome to NetWiz YouTube channel. Today I'm going to continue with my Noti series of videos, and in this one I'm going to look at Ospf, more precisely Ospf neighbor relationships. And I'm not doing it because it brings any benefit or has any use in production environment, but just because I'm curious and because breaking stuff is fun. So we're gonna have a look at the topology first. I've got three routers, R1, R2, and R3, and I'm going to see if I can make R1 and R2 to become OSPF neighbors, and I will be using their physical interfaces, not tunnel interfaces, to do that. And the difficulty with that is they have R3 sitting between them, so it's definitely not a standard or a recommended configuration, but we'll see if that is possible. So the network I'll be using is 192.168.1.0/24, and here we come across our first problem. Now, while I can configure that network on Ethernet 0, 0 interfaces on both R1 and R2, R3 cannot have the same subnet configured on two of its interfaces. So that kind of dictates our first move, and I'm going to split the network 192.168.1.0/24 into 2/25 networks to assign them subnets on R3's interfaces. So let's do that first. We'll go to R3 and configure its Ethernet 00 interface with IP address of 192.168.1.3/25 and interface Ethernet 01 with IP address of 192.168.1.253/25. Now R1 and R2 will be on a /24 subnet. 1.14 R1 and we're going to have to use a high IP address for this one. 252. No shutdown. Okay. So that now our interfaces are up. We should be able to ping from R1 to R2 because by default in this version of iOS, the proxy ARP is on by default. And we're going to test that from R1 to R2. And finally, when I remember to bring up interface on R3, we are pinging between R1 and R2. Cool. So first obstacle overcome. We've got the IP reachability between R1 and R2. The next step is to enable the OSPF process and configure our network to become included in that OSPF process. But before I do that, just to have full visibility of what is happening step by step, I'm going to turn on debugging of Ospf adjacencies and hello packets on R1 and R2. And I'm going to turn on debugging of all IP packets on R3. Great, so let's carry on with OSPF configuration. I'm going to be only using area 1 on both of them. Right, so that is done. We can see that our OSPF process have initiated, and Ethernet 00 interface became part of this process. And we can also see that we are sending hello to address 224.0.0.5 in array 0 on in Ethernet 00 interface. But we can also see that we do not receive any hello packets back. Now I'm gonna look at our packet capture and see what happens with these packets. We can see the packets are being sent, but if we expand their IP header, we can see that they are sent with a TTL of 1. That is the default TTL for Ospf packets, and also it's the default TTL for 224.0.0.0/24 multicast range. So what we can do now is we can disable the TTL security feature on OSPF to make sure that we send our hello packets with a higher TTL than 1. So let's do that on R1 and R2, and that is the interface level configuration. And I'll say TTL security hops and set it equal to 10. Oops, 10. Okay. Now if we go back to our packet capture and take another one, we can see that our time to live is now set to 255, even though I've configured it to be 10. But when it turns off the IPOSPF TTL security mechanism, it just ramps it up all the way to 255. But we can see that we're still not receiving any hello packets, even though the TTL is now higher than 1, and the packets should make it through the router. Now let's have a look at what happens to them hello packets on R3. We see that we are debugging it, and it says that the packet to destination 224.0.0.5 is unroutable, and that is because by default, again, 224.0.0/24 is a receive entry in the forwarding table. So R3 on receiving the packets for this IP address just consumes them and doesn't forward them any further. To overcome this, we need to stop using the multicast addressing. So we need to switch to using a unicast address, and we can do that by configuring neighbours in OSPF, although this option is only available for non-broadcast networks. So next thing we need to do is we need to convert our network type into a non-broadcast one on R1 and R2. Okay, now we can see that we are going through the election of DR and BDR, which also happens on non-broadcast networks, but we haven't configured our neighbors yet. So let's go into OSPF process and do our neighbor configurations. Right, so we are restarting the process, and let's see if it establishes this time. Let's have a look at our OSPF neighbor state. Now we can see that we are getting to a two-way state. So that means our hellos are being received by a neighbor and the neighbor acknowledges their receipt. So that's good. We already see some communication on OSPF process. Let's wait a little bit and see if that goes all the way to established, to full. And there we go. A few seconds more, we can see that we've got loading to full. And if we look at Ospf neighbor state, yes, we can definitely see that we've got our neighbor relationship established. To test that, what I'm going to do now is I'm going to create a loopback interface. I'm going to turn off debugging now. And I'm going to create a loopback interface, give it a random IP address and redistribute it into Ospf to see whether we will receive that on R2. And we go back to R2 and do show IP route. Not there yet. And finally, we can see that our external type 2 route appears in Ospf. Now, the question is, what will happen if I try to ping 1.1.1.1 from R2? Will it work or will it fail? Let's have a look. And as expected, it failed. And it failed because we still have R3 in the middle, which knows nothing about 1.1.1.1. So although we've got fully functional Ospf neighbor relationships and we can have route exchange happening between R1 and R2, R3 is still a valid layer 3 hop in between them, and to route to any of these destinations, it still needs to know about them. So how do we overcome this obstacle? Well, we simply can create a static route on it. With the next hop pointing to 192.168.1.1. And then when we try to ping 1111 from R2 again, this time it worked fine. Again, as I said, there is no practical use to it. As you can see, we still defy the whole purpose of dynamic routing by having to introduce static routes on the hop in the middle. But that was an interesting exercise and an interesting lab experiment to see how far we can get with, bending and breaking some of the rules. I hope it was interesting for you and thank you for viewing. There's definitely more of this fun stuff to come, so stay tuned. Until next time.